Section 1 Introduction. We're opening this paper by discussing how language models are usually trained. These models are taught to predict the next word or phrase in a sequence, on a very large scale. This way, they learn how to understand and generate language in a way that's useful for many different tasks. Several techniques have been developed to make these models more efficient, the most popular ones being instruction tuning, which involves training on large datasets, and reinforcement learning from human feedback, where feedback from millions of interactions with human annotators is used for training. To get a model that performs at the same level as ChatGPT, one would typically need a lot of computational resources and specialized data. However, we found something interesting. With a strong pre-trained language model, great performance can be achieved by simply fine-tuning it on just 1,000 carefully selected examples. We believe that the process of making a model align well with user needs can be simple. The model just needs to learn the specific style or format of interacting with users, in order to use the knowledge and abilities it acquired during pre-training. To put this idea to the test, we've created 1,000 examples that are similar to real user prompts and high-quality responses. To make our sample, we chose 750 top questions and answers from community forums like Stack Exchange and WikiHow, ensuring we had a good mix of quality and diverse content. We also wrote 250 examples of prompts and responses ourselves, focusing on making sure the tasks were varied and the responses followed a uniform style, similar to how an AI assistant would respond. Then, we trained LIMA, a model that was pre-trained and had 65 billion parameters, using our set of 1,000 demonstrations. We tested LIMA against leading language models and products, using 300 challenging test prompts. In a study where humans expressed their preferences, we found that LIMA performed better than DaVinci 003, which was trained using reinforcement learning from human feedback, and Alpaca, which was trained on 52,000 examples. People usually preferred responses from GPT-4, Claude, and Bard over LIMA, but not always. LIMA produced responses that were either as good as or better than the other models in 43%, 46%, and 58% of cases, respectively. When we repeated the study with GPT-4 doing the evaluating, the results were similar. When we looked at LIMA's responses in more detail, we found that 88% of them met the requirements of the prompt and 50% were considered excellent. We also found that when we increased the amount of data we used for training but didn't also increase the variety of the prompts, the improvements were much smaller. However, when we improved the quality of the data, the improvements were significant. Even though LIMA didn't have any examples of dialogue to learn from, it was able to carry out multi-turn dialogues that made sense. When we added just 30 handcrafted dialogue chains to the training set, LIMA's ability to handle dialogues improved dramatically. These findings highlight the power of pre-training and show that it's more important than large-scale instruction tuning and reinforcement learning approaches in certain contexts. Section Summary. The section discusses the effectiveness of fine-tuning a pre-trained language model on a carefully curated set of 1,000 examples for language alignment, as opposed to using large multi-million example datasets or reinforcement learning from human feedback. The resulting model, LIMA, outperforms state-of-the-art language models and products in a human preference study, with 88% of its responses meeting prompt requirements and 50% considered excellent. The study also shows that prompt diversity and data quality are more important than data quantity for achieving strong performance. Section 2 Alignment Data. Our discussion here revolves around the concept we refer to as the superficial alignment hypothesis. This idea proposes that a model predominantly gains its abilities and understanding during the pre-training phase, while the alignment stage helps the model learn the optimal sub-distribution of formats to use when interacting with users. Essentially, alignment is seen primarily as a process of style acquisition. Building on this hypothesis, we suggest a corollary that a pre-trained language model could be adequately fine-tuned using a relatively small collection of examples. In line with this, we assembled a dataset comprised of 1,000 prompts and responses. We ensured that while the prompts varied widely, the responses maintained a consistent stylistic alignment with each other. In particular, we sought responses that mirrored the tone and manner of a helpful AI assistant. We gathered these examples from a diverse array of sources, but primarily from community Q&A forums and examples that we manually authored. Additionally, we assembled a test set consisting of 300 prompts and a development set made up of 50 prompts. A table detailing the various sources of our data, along with some accompanying statistics, can be found later in the paper. For a sampling of the training examples we used, refer to the appendix. Section Summary. The superficial alignment hypothesis suggests that a model's knowledge is learned during pre-training, while alignment teaches it which sub-distribution of formats to use when interacting with users. This means that a pre-trained language model can be sufficiently tuned with a small set of examples. To test this, the authors collected a dataset of 1,000 prompts and responses, where the outputs are stylistically aligned with each other, but the inputs are diverse, and curated examples from community Q&A forums and manually authored examples. Section 2.2.1 Gathering community questions and answers. Our data collection process involves three major community Q&A platforms: Stack Exchange, WikiHow, and the Push-Shift Reddit dataset. Broadly, answers from Stack Exchange and WikiHow align well with the expected conduct of a supportive AI agent, allowing us to extract information automatically. However, Reddit's most upvoted responses often contain humor or trolling elements, necessitating a more hands-on method to select responses that suit the intended style. Stack Exchange. The Stack Exchange platform is comprised of 179 digital communities or exchanges, each focusing on a distinct topic. The most frequented one is dedicated to programming, known as Stack Overflow. The platform allows users to post questions, responses, comments, and cast votes on all posted content. The active engagement of its community members and moderators has helped Stack Exchange maintain a high standard of content quality. To ensure the quality and variety of our data from Stack Exchange, we apply specific measures. Initially, we categorize the exchanges into 75 STEM exchanges, encompassing fields like programming, mathematics, physics, and so on, and 99 other exchanges that include English, cooking, travel, among others. We dismiss 5 exchanges due to their niche nature. From each category, we draw 200 questions and answers, using a parameter known as temperature set to tau equals 3, which aids in obtaining a balanced sample from the various domains. Within each exchange, we choose questions that are both high-scoring and self-contained within the title. The top answer for each question is then selected, provided it has garnered a considerable positive score, typically at least 10. Keeping in line with the style of a helpful AI assistant, we filter out responses that are excessively brief, less than 1,200 characters, overly long, more than 4,096 characters, or written in the first person, using I, my. We also disregard answers that refer to other responses, as mentioned, Stack Exchange, and so on. Further, we eliminate any links, images, and other HTML tags from the response, preserving only code blocks and lists. Since Stack Exchange questions consist of both a title and a description, we choose either the title or the description randomly as the prompt for some examples. Section Summary. The authors collected data from 3 community Q&A websites: Stack Exchange, WikiHow, and the Push-Shift Reddit dataset. Stack Exchange was the most reliable source due to its high content quality and active moderation. They applied quality and diversity controls when sampling from Stack Exchange, filtering out short or long answers, first-person references, and links, and retaining only code blocks and lists. Section WikiHow. We chose to utilize 2 primary sources for our research: WikiHow and the Push-Shift Reddit dataset. WikiHow, an online resource that provides thousands of guides on a vast range of topics, was the first one. This platform allows anyone to contribute, and the content is thoroughly moderated, which results in high quality and reliable information. We selected 200 articles from WikiHow, ensuring diversity by first choosing a category from a total of 19 and then picking an article within the chosen category. Each title of the article, such as How to Cook an Omelette, was used as a prompt, and the body of the article served as the corresponding response. To make it fit for our study, we made some modifications, like replacing the initial "this article" with "the following answer," and removing elements like links, images, and specific text sections. The second source was the Push-Shift Reddit dataset, stemming from Reddit, a popular website where users can share, discuss, and vote on content. Reddit's user-generated subgroups, called subreddits, are often more entertainment-focused, with clever or humorous comments often attracting more attention than serious or informative ones. Therefore, we decided to restrict our sampling to 2 subreddits, r Ask Reddit and r Writing Prompts, choosing examples from the most upvoted posts in each group. From r Ask Reddit, we selected 70 standalone prompts, without any additional text body, to be used for our test set, considering that the most upvoted responses might not be consistently reliable. On the other hand, the Writing Prompts subreddit provided us with story starters, encouraging other users to complete the narrative in a creative way. We harvested 150 such prompts along with their high-quality responses, covering themes from love poems to short science fiction stories, which were added to our training set. All these data points were extracted from the mentioned Push-Shift Reddit dataset. Section Summary. The authors of the paper collected data from 2 sources, WikiHow and Reddit. They sampled 200 articles from WikiHow, using the title as the prompt and the article's body as the response. They also manually selected Examples from the most upvoted posts in r AskReddit and r Writing Prompt subreddits, restricting the sample to 70 self-contained prompts from r AskReddit for the test set and 150 prompts and high-quality responses from r Writing Prompts for the training set. Section 2. In Section 2.2, we describe our approach for adding variety to our data, which is largely composed of queries from online communities. In order to achieve this, we divided the authors of this study into two groups, Group A and Group B. Each group was tasked with developing 250 original prompts inspired by their personal interests or those of their friends. Even though we tried to avoid overlap, some communication between the two groups occurred before the annotation process. As a result, some common themes emerged within the data. We then selected 200 prompts from Group A for training purposes and reserved 50 for a development set. After removing a few problematic prompts, we used the remaining 230 from Group B as test material. To further enrich the training set, we paired the 200 prompts with high-quality answers that we drafted ourselves. Our goal was to maintain a consistent and helpful tone, similar to what you would expect from an AI assistant. Typically, a prompt was addressed with an initial acknowledgement of the question, followed by the answer itself. We found that this format tended to enhance model performance, likely because it helps the model develop a logical sequence of thought, akin to a step-by-step approach. We also included 13 training prompts that had elements of hostility or harm. We carefully crafted responses that either partially or entirely rejected the request, providing an explanation for the refusal. An additional 30 such prompts were included in the test set, and these are discussed further in section. Alongside our handcrafted examples, we introduced 50 training examples from a resource called Supernatural Instructions. These examples encompassed a variety of language generation tasks such as summarization, paraphrasing, and style transformation. We chose one random example from each category and slightly modified some of them to align with the style of our manual examples. While the types of prompts a user might pose might not match exactly with the tasks in Supernatural Instructions, our intuition was that introducing this selection could add to the diversity of training examples and potentially enhance model resilience. Crafting diverse prompts and generating thoughtful responses in a consistent style is quite a demanding process. Recent studies have looked into ways of automating this task to produce larger quantities of data, but we chose to prioritize the quality and variety of our inputs instead, to explore the potential benefits of this approach. Section Summary. The authors of the paper collected prompts from themselves to diversify their data beyond questions asked by users in online communities. They designated two sets of authors to create 250 prompts each, with 200 prompts from Group A used for training and 50 prompts as a held-out development set. They supplemented the training prompts with high-quality answers, which they wrote themselves, and included prompts with toxicity or malevolence to explain why the assistant will not comply. They also sampled 50 training examples from Supernatural Instructions to add diversity to the overall mix of training examples. Section 3. Training LIMA. We train our model, LIMA, less is more for alignment, using a specific process. This model begins with a base of LLaMA 65B and is fine-tuned using a set of 1,000 examples for alignment training. We've incorporated a unique end-of-turn token, or EOT, to clearly distinguish between each speaker's turn. This could be a user or an assistant. This token works like an end-of-sentence token, signaling the end of generation, but it doesn't interfere with any existing meanings that the pre-trained model might have assigned to the original end-of-sentence token. The fine-tuning of the model follows standard protocols. We fine-tune it for 15 iterations, or epochs, using a particular optimization algorithm called AtomW. The parameters for this optimizer are set with first moment values of 0.9, second moment values of 0.95, and a weight decay value, which is a method to prevent overfitting, of 0.1. The learning rate, which is a measure of how much the model changes in response to the perceived error each time it is updated, is set to start at 1E5 and decrease linearly to 1E6 by the end of the training process. In terms of batch size, we've set it to 32 examples for large models and 64 for smaller ones. Any texts exceeding 2048 tokens in length are shortened to fit within this limit. One thing we do that deviates from common practice is the application of dropout to residual connections. Dropout is a technique to prevent overfitting by randomly setting a fraction of input units to 0 during training. Starting from the bottom layer, we set the dropout rate to 0.0 and gradually increase it linearly to 0.3 by the final layer for larger models, and 0.2 for smaller models. Interestingly, we found that a lower perplexity score, which is often used to gauge a model's performance, doesn't necessarily equate to better quality generation. Therefore, we manually select checkpoints for the model between the 5th and 10th epochs using a separate set of 50 examples for development. A more detailed comparison between validation perplexity and generation quality can be found in the appendix. Section summary. The LIMA model is trained by fine-tuning on a 1000 example alignment training set, using a special end-of-turn token to differentiate between speakers. Standard fine-tuning hyperparameters are followed, with the exception of residual dropout, and checkpoints are manually selected based on generation quality rather than perplexity. Section 4. Human evaluation. Section 4. Human assessment. In this section, we evaluate our model, LIMA, by comparing its performance with that of cutting-edge language models. We discovered that LIMA excels over the RLHF-based DaVinci 003 developed by OpenAI, and a reproduction of Alpaca using 65 billion parameters, which was trained with 52,000 examples. LIMA often matches or even surpasses GPT-4 in terms of the quality of its responses. By analyzing LIMA's outputs, we found that half of them are deemed outstanding. This significant performance achieved with simple fine-tuning using a relatively small number of examples aligns strongly with the superficial alignment hypothesis. It serves as an excellent example of the efficacy of pretraining and underscores its importance in comparison to large-scale instruction tuning and reinforcement learning methods. 4.1 Experiment Framework. In order to gauge the performance of LIMA against other models, we designed an experiment where a single response is generated for each test prompt. We then invited crowd workers to compare the responses produced by LIMA with those from our baseline models and choose the one they favored most. We conducted the same experiment substituting the human crowd workers with GPT-4 and found similar levels of agreement. We compared LIMA's performance with that of 5 other baseline models. 1. Alpaca 65B. For this model, we fine-tuned Llama 65B using 52,000 examples from the Alpaca training set. 2. OpenAI's DaVinci 003. This is a large language model that has been trained using reinforcement learning from human feedback, RLHF. 3. Google's Bard. This model is built on the Palm platform. 4. Anthropic's Claude, a 52 billion parameter model that was trained using reinforcement learning from AI feedback, a method known as constitutional AI. 5. OpenAI's GPT-4. This large language model was trained with RLHF and is presently deemed the state of the art. The responses from these baseline models were collected over the course of April 2023 for comparison. Section summary. The performance of LIMA was evaluated against state-of-the-art language models, including OpenAI's DaVinci 003 and a 65B parameter reproduction of Alpaca, and was found to often produce better or equal responses than GPT-4. 50% of LIMA's outputs were considered excellent, demonstrating the power of pre-training and supporting the superficial alignment hypothesis. The evaluation was conducted by generating a single response for each test prompt and asking crowd workers to compare LIMA outputs to each of the baselines. Section: Generation. In the generation phase of our process, each baseline model provides one response for every prompt. We accomplish this through nucleus sampling with a set parameter, p, of 0.9, and a specified temperature, tau, of 0.7. To discourage repetition, we use a penalty of 1.2 for previously generated tokens. We also cap the token length at 2048. When it comes to our methodology, at every step, we present a single prompt to the annotators along with 2 potential responses that have been created by separate models. The annotators then decide which response is superior, or if there isn't a clear winner. You'll find the specific wording we use in the appendix. We also carried out identical steps with GPT-4, giving it the same instructions and data for comparison. We determine the level of agreement between annotators using a method called tie-discounted accuracy. The basic idea is that we award 1 point when both annotators concur, half a point when only one annotator perceives a tie, and no points when they completely disagree. We calculated these scores using 50 shared annotation examples, featuring a single prompt and 2 model responses, and we compared the scores of author annotations, crowd annotations, and GPT-4 annotations. We discovered that the agreement scores among human annotators were fairly consistent: 82% for crowd to crowd, 81% for crowd to author, and 78% for author to author. Even though there's some subjectivity in this task, the agreement among human annotators is relatively good. We also assessed the agreement between GPT-4 and human annotators. Here, the figures were 78% for crowd to GPT and 79% for author to GPT. It's worth noting that even though we utilized stochastic decoding, GPT-4 nearly always agreed with itself. These statistics show that GPT-4's level of agreement is on par with that of human annotators. This could be seen as an indication that GPT-4 essentially passes the Turing test for this particular task. Section summary. The authors used nucleus sampling with p equals 0.9 and a temperature of tau equals 0.7 to generate a single response from each baseline model. They presented annotators with a prompt and two possible responses, generated by different models, and asked them to label which response was better. The inter-annotator agreement was decent among human annotators, with crowd-crowd agreement at 82%, crowd-author at 81%, and author-author at 78%. GPT-4 also showed agreement with human annotators, with crowd GPT at 78% and author GPT at 79%. Section 4. Looking at the results of our studies, as depicted in our illustrations, we find some intriguing patterns. The first part of our discussion focuses on the human preference study, as the preferences of the GPT-4 model largely mirror these trends. An interesting point we noted is that despite being trained on a dataset that is 52 times larger, the model we've named Alpaca 65B typically produces results that are less favored than those generated by a model we call LIMA. This phenomenon also appears with DaVinci 003, although it's not as pronounced. What's surprising here is that DaVinci 003 was trained using RLHF, a training method typically seen as more advanced and effective. However, we see a contrasting trend with the BARD model. This model tends to produce better responses than LIMA around 42% of the time. But this implies that for the remaining 58%, LIMA's outputs are deemed at least as good, if not better. Examining Claude and GPT-4, while they generally outperform LIMA, there's a significant number of instances where LIMA's responses are superior. Adding a touch of irony, even GPT-4 appears to prefer LIMA's outputs to its own in 19% of the cases. Moving on to the analysis, our primary evaluation compares LIMA with other cutting-edge models. However, it's important to note that some of these comparison models are exceptionally fine-tuned systems. They may have been trained with millions of real user prompts, which sets a high benchmark for performance. For a more standalone evaluation of LIMA, we manually analyzed a random set of 50 examples. We categorized each example into one of three groups: fail, where the response didn't meet the prompt's requirements; pass, where the response satisfied the prompt's requirements; and excellent, where the model provided an exceptional response to the prompt. Section summary. The study compared the performance of various language models, including GPT-4, Alpaca 65B, DaVinci 003, BARD, Claude, and LIMA. Despite being trained on 52 times more data, Alpaca 65B tended to produce less preferable outputs than LIMA. While Claude and GPT-4 generally performed better than LIMA, there were still cases where LIMA produced better responses, even preferred by GPT-4 19% of the time. The study also provided an absolute assessment of LIMA's performance through manual analysis of 50 random examples. Section: Results. Looking at our findings, we can see that the LIMA model performs quite well. If we refer to the figure in the paper, it reveals that half of LIMA's responses are deemed excellent, and the model effectively addresses all but 6 of the 50 prompts we've examined. Interestingly, we didn't find any clear pattern in the instances where it fell short. The figure further demonstrates the versatility of LIMA by illustrating its outputs when asked for parenting advice or when tasked with generating a recipe. We also delved into how LIMA performs outside of its comfort zone, or out of distribution. We analyzed 50 examples, out of which 43 bore some similarities to the training examples in terms of format, such as question answering, advice giving, and letter writing. Then, we explored an additional 13 out of distribution examples, making the total 20. Our findings indicate that 20% of LIMA's responses fell short, 35% passed, and 45% were excellent. While this is just a small sample, the results hint that LIMA's performance remains stable even outside of its training distribution, suggesting good generalization capabilities. This is clearly illustrated in the figure where LIMA was asked to write a stand-up routine or place a pizza order. Lastly, we examined the model's safety performance. We know that there were only a few safety-related examples in the training set, just 13, and we wanted to see how this affected the model's responses. When we tested LIMA with 30 potentially sensitive prompts, we found that it provided safe responses to 80% of them. This included successfully navigating 6 out of 10 prompts that had an undercurrent of malicious intent. In certain scenarios, LIMA outright refuses to execute the task. For instance, if asked to divulge a celebrity's address, the model won't comply. However, we noted that if the harmful intent is more subtly incorporated into the prompt, LIMA is more likely to generate unsafe responses. You can see this dynamic illustrated in the figure in the paper. Section summary. The study found that LIMA performs well on prompt-following tasks, with 50% of answers considered excellent and only 6 out of 50 prompts not followed. Out-of-distribution examples showed similar performance statistics, with 20% of responses failing, 35% passing, and 45% being excellent. LIMA also responds safely to 80% of potentially sensitive prompts, including 6 out of 10 prompts with malicious intent. Section 5. Why is less more? Ablations on data diversity, quality, and quantity. In this section, titled 5. Why is less more? Ablations on data diversity, quality, and quantity. We take a closer look at the impact of various attributes of training data, diversity, quality, and quantity, on the alignment process. Our findings suggest that increasing the variety of inputs and the quality of outputs has a clear positive effect. However, merely increasing the amount of data may not be as effective. In our experimental setup, we adapted a LLaMA model with 7 billion parameters across different datasets, while keeping the same hyperparameters consistent. Initial tests indicate that while we can adjust the 7 billion parameter model using only 1,000 examples, a sample size of at least 2,000 examples seemed to promote more stability. To evaluate the quality of responses, we generated 5 responses for each test prompt. Then, we enlisted the help of ChatGPT, GPT 3.5 Turbo, to rate the usefulness of the responses on a scale of 1 to 6. The final score reported is an average of these ratings, and we provide a 95% confidence interval around this average. To study the impact of prompt diversity, we compared 2 sets of high-quality data, Stack Exchange and WikiHow. Stack Exchange offers a wide range of prompts with high-quality responses, while WikiHow tends to have similar types of prompts with equally high-quality responses. Using these platforms as representative of diversity, we selected 2,000 training examples from each source. While we acknowledge that there could be other variables at play when gathering data from 2 different sources, our analysis revealed that the more varied Stack Exchange data resulted in noticeably better performance. Section Summary. The paper investigates the effects of training data diversity, quality, and quantity through ablation experiments. The authors found that increasing input diversity and output quality have positive effects on alignment, while increasing quantity alone may not. They also found that training on more diverse data, such as Stack Exchange, leads to significantly higher performance compared to homogeneous data like WikiHow. Section Quality. We evaluated how the quality of responses affects our model by using 2,000 examples from Stack Exchange without any specific quality or stylistic filters. We then compared this model to one that was trained using a carefully filtered dataset. Our analysis revealed that models trained on refined data yielded significantly better results by about half a point compared to models trained on unrefined data. When it comes to the quantity of examples, it's common knowledge that in many machine learning scenarios, increasing the number of examples tends to enhance performance. However, our tests using progressively larger training sets from Stack Exchange demonstrated something surprising. Simply doubling the training set did not yield better quality responses. Based on this and other findings, we concluded that the alignment scaling laws in our context are influenced not merely by the sheer number of examples, but also by the variety of prompts coupled with high-quality responses. We also conducted an experiment to determine if a model fine-tuned with only 1,000 single-turn interactions could engage in multi-turn dialogue. We tested our model, which we named LIMA, across 10 live conversations. In these tests, we classified each response as either fail, pass, or excellent. Although LIMA was a zero-shot chatbot, its responses were remarkably coherent, referencing information from previous steps in the dialogue. However, it was also clear that the model was working beyond its intended scope. In 6 out of the 10 conversations, LIMA lost track of the dialogue within 3 interactions. To enhance LIMA's conversational capabilities, we assembled 30 multi-turn dialogue chains. These included 10 dialogues composed by us and 20 dialogues adapted from comment chains on Stack Exchange, revised to match the chatbot style. We then fine-tuned a new version of LIMA based on a pre-trained model called LLaMA, using the combined 1,030 examples. We conducted another 10 live conversations using the same prompts as with the zero-shot model. The addition of conversation examples significantly boosted the quality of the generated responses, with the proportion of excellent responses increasing from 45.2% to 76.1%. The rate of failure also decreased substantially, dropping from 15 out of 42 turns in the zero-shot model to just 1 out of 46 in the fine-tuned model. We compared the overall quality of the dialogues and found that the fine-tuned model outperformed the zero-shot model in 7 out of 10 conversations, and was on par with it in the remaining 3. This notable improvement, despite only adding 30 examples, as well as the fact that the zero-shot model was able to converse at all, strengthens our hypothesis that such abilities are acquired during pre-training and can be brought to the fore through limited supervision. Lastly, we experimented with the removal of specific tasks from our dataset. We found that even just 6 examples can significantly affect the model's ability to generate complex structured text, as detailed in the appendix. Section Summary. The study tests the effects of response quality and quantity on machine learning models trained on Stack Exchange data. The results show that prompt diversity and maintaining high-quality responses are more important than quantity alone. Additionally, fine-tuning a model on just 30 multi-turn dialogue chains significantly improves generation quality, reinforcing the hypothesis that such capabilities are learned during pre-training and can be invoked through limited supervision. Section 7 Discussion. Point 7 Discussion. Our research reveals that refining a potent pre-existing language model with just 1,000 meticulously selected instances can yield exceptional and competitive outcomes across various prompts. But this method is not without its drawbacks. First and foremost, the intellectual strain involved in crafting these instances is substantial and challenging to expand. Additionally, LIMA doesn't possess the resilience of commercially viable models. Though LIMA usually delivers solid results, an unfortunate sampling during the decoding phase or a maliciously crafted prompt may sometimes result in a subpar response. Despite these limitations, the evidence put forth in this study shows the potential of addressing intricate alignment issues with a straightforward strategy. At training examples. The figure displays 6 instances utilized for training sourced from different datasets. B. Relationship between perplexity and quality of generation. When we fine-tune LIMA, we notice a negative correlation between perplexity on the Stack Exchange data withheld for testing, composed of 2,000 examples, and the model's capacity to generate high-quality responses. To put a numerical value on this observed pattern, we evaluate the model's outputs using ChatGPT, adhering to the procedure outlined in a previous section. The figure shows that as perplexity increases with more training iterations, which is usually an indicator of the model overfitting, the quality of the generated content also improves. As we lack an inherent method of evaluation, we therefore rely on manual checkpoint selection using a modest validation set of 50 examples. Section Summary. The authors demonstrate that fine-tuning a strong pre-trained language model on 1,000 carefully curated examples can produce remarkable, competitive results on a wide range of prompts. However, there are limitations to this approach, including the significant mental effort required to construct such examples and the fact that LIMA is not as robust as product-grade models. The authors also observe an anti-correlation between perplexity and generation quality when fine-tuning LIMA. Section C. Human Annotation. In Section C, we outline the human annotation interface used to gather preference judgments. We asked our annotators to empathize and imagine they were the ones who originally provided the prompts. In Section D, we touch on the complexity of automatically assessing generative models. We utilize ChatGPT, specifically its 3.5 turbo version, for ablation experiments. We evaluated the model's outputs using a 6-point Likert scale, based on the prompts provided, which are shown in figure. In Section E, we delve into generating text with intricate structures. We noticed that our model, LIMA, performed well in responding to a broad range of questions from our development set. However, it struggled to consistently deliver when asked to provide answers with a specific structure, like turning an article into bullet points or crafting an article around certain key elements. We wondered if including a few training examples with similar demands might help LIMA better understand and cater to unseen structural requirements. So, we incorporated 6 training examples that had different formatting constraints. For instance, generating a product page which includes sections like highlights, about the product, and how to use or crafting question-answer pairs based on a given article. After training with these additional examples, we tested LIMA on several questions with formatting constraints. The results were promising. LIMA's responses significantly improved. In figure, we have provided 2 examples. These show that without training examples focused on structure, LIMA struggles to provide apt answers, left column. But with such training, LIMA can generate highly complex responses, like a marketing plan, even though we don't have any specific examples of marketing plans in our data, right column. Section Summary. The authors used a human annotation interface to collect preference judgments and evaluated generative models using ChatGPT. They found that their model, LIMA, struggled to consistently respond to questions that specified the structure of the answer, but after adding training examples with formatting constraints, LIMA's responses greatly improved and it was able to generate complex responses such as a marketing plan even without specific examples in the